Okay, so office hours week 6. We're going to start with some review from quiz 3, problems 2 and 3. What's problem 2?
Okay, this one's kind of long, but 51.07 micromolarity dye sample has an absorption of A equals 0.774 at the wavelength max of 580 nanometers. What is the apparent color of the dye, and what is the molar absorptivity of the dye?
Oh, what was the wavelength? Sorry, we actually need the wavelength for what color?
Yeah, it was 580 nanometers.
Okay.
And then it's if a second sample of the same dye has a concentration of 27.67 micromolarity, what would the absorption be of the second sample?
You said 27.67 micromolarity. Okay. So, I didn't write down all of the words because it takes too long to write everything down, but let's go ahead and look at this. So we've got a sample. We've got a concentration, an absorbance, a wavelength. We're asked for epsilon. In terms of our information, focusing on key terms, we want to say, okay, what gives us a clue for what kind of problem this is? Anytime we're seeing molar absorptivity, it's a Beer's law problem, right? And you want to create that type of mapping in your head where when you see certain terms, certain variables, you're just like, oh, I know what that's going to be. So we know this is going to be A equals epsilon BC. Doesn't say anything about path length, so I assume that's 1. The concentration is going to be 5.0. It was 5.07, right? Or was it 50.7?
It was 51.07.
Okay, I missed a digit there. 51.7, let's fix that real quick. 51.7 micromolarity. Does it ask for absorbance in molarity or micromolarity? Or sorry, molar absorptivity.
Molar absorptivity.
What are the units on that below the box?
Molarity.
Okay, so we have to do one quick conversion where I'm going to do 1 times 10 to the minus 6 molarity for every 1 micromolarity. And I'm going to do that conversion kind of a lazy way, so I've got 0.774 equals epsilon times 1 times 51.07 times 10 to the minus 6. Your calculator will make that like 5.1 times 10 to the minus 6 times 10 to the minus 5. But this, I like where I can still see the 51. So for solving for epsilon, we just divide over. Notice we don't need the wavelength here. Right? The wavelength is essentially like a reference system, where as long as the wavelength isn't changing, it's fine. We only need to worry about wavelength if it's changing in the problem. If it's changing in the problem, something really weird is happening, like we saw in the midterm, where it's like, oh, the chemical compound must be changing. It must be a different chemical compound, because that's really what changes that. So to get the epsilon is kind of just doing some division and stuff like that. That's going to get us the epsilon. That's that part. If we want to get the second sample, that's going to be, now we don't know absorbance, we can use that epsilon in there times 1 times 27.67 times 10 to the minus 6. Right? Again, doing my quick little conversion, I'm just doing that bit in my head. So that's going to get us that bit. So we can do those two calculations. The important part was to realize that it was a Beer's law problem, and then it was just making sure we converted our units properly. Now, when we do this calculation, I can already tell you in this second one, if the concentration is about half, the absorbance should be about concentration down by a factor of 2, absorbance goes down by a
factor of 2.
By about a factor of 2, right? Because absorption and concentration directly relate to each other. If our concentration cuts in half from about 51 to about 27, it's not exactly half, but it's about half. This 0.77, I'm going to guess that it goes to like 0.35. Well, it's probably going to go to like 0.38, something like that. So I've got a ballpark of what I'm expecting it to be. Does anyone remember the value range of epsilon that we typically see as well?
10,000 to something.
That's like
5,000.
10,000 to 100,000 is our typical value. So as we look at this, we can go ahead and see if we get things that make sense for that. So here's the wild part about this. When we get to doing the math, and this is where what I said before I started recording becomes really important. It's the conceptual thinking of how we set everything up is the important part. The math is just this. That's all the math we have to do. Can you divide two numbers? Yeah, of course you can, right? Especially because you don't even have to do it by hand. You got calculators, right? The math itself is not the hard part of the problem. Most people focus on the math because, you know, it's a quantitative, chemistry's quantitative. We usually like to get numerical values. But at this level that we're working, it's really the numbers are not the important thing. It's the meaning of the numbers, right? It's the, like, I don't need to know the specific value of epsilon. The fact that there's a reasonable range and the fact that it's telling us about how much light is absorbed, that understanding level is kind of the important part here. So let's go ahead and figure this out real quick. 0.774 divided by 51.07 times 10 to the minus 6. We get something that is like 15,000, still above the 10. But we get epsilon is equal to 15156 times 10 to the positive 4. So it's 1.5156, 15,156. And then I just dump that in there to solve for my new absorbance. So I'm going to take that and multiply by 27.6 times 10 to the minus 6. A little bit higher than, what number was I predicting?
0.38.
0.38 ends up being 0.41.
Close enough.
Not that far off, 418, right? So not that far off, but for a complete, like, no calculation, just eyeballing it, using the concepts to inform what value I expect, pretty good. For the color, this is where I need to look at a rainbow. Oh, here we go. Okay. Well, let me look at mine because the one I have on the front of the exam has like the wavelength ranges as well. I don't know if you noticed that there was like a. I don't think we even needed it on this exam, but I always include it. 580 nanometers would be someplace in the yellow range, which means if it's absorbing yellow, it appears purple. Okay, so this is going to look purple. And that's an important distinction. The wavelength absorbed versus the appearance can be different from each other. And that's something that is challenging a past kind of misconception a lot of us have from high school, where something looks a particular color because it's reflecting that color. Something is green because it's reflecting green light. And it's like, no, something was green because it's absorbing red light. Could be, it's reflecting green, but it's also reflecting yellow, blue, purple, right? It's reflecting more than just green. But our brain, the way that our brain does the interpretation of wavelengths, it looks green to us because green's kind of in the middle of all the wavelengths. Good pace? Too fast? Too slow? Other questions? Related? Yeah.
0.418, that represents the nanometers?
No, that's the absorbance of the new absorbance for the second part. If second sample had that concentration, that's the new absorbance.
Okay.
And it's about half of what we had before because our concentration's about half. And so that conceptual understanding of how concentration relates to absorbance is actually the important part, not just the numbers. So as you're doing homework assignments, as you're doing quizzes, as you're doing exams, you always want to have a little bit of reflective time to be like, what's important about the number I just got? What's the meaning of the number I just got? How does it relate to other problems? Not just, I got the right number, I got my green box, great, moving on, but like, why did that work? How did I get it to work? What's really going on here? Ready for number 3? Okay. Okay. So notice again in that we didn't really need the wavelength besides the apparent color. But if the wavelength changed, the absorptivity would change, the epsilon would change. Quiz 3, number 3.
A dye has a molar absorptivity of 4.57 times 10 to the 4th molarity, Cn, and a molar mass of 796.1 grams per mole.
796.1?
What mass of green dye would you need to prepare 1.74 liters of the solution with an absorbance of 0.585?
0.585?
Yes.
Okay. Come on in, come on in.
Is there any other seats?
Are you comfortable sitting on the floor or the desk?
Thank you.
You bet. Okay. So, let's take a look here. So, another Beer's Law problem. So what we got here is we say, okay, how do I know it's a Beer's Law problem? Gave me an epsilon, molar absorptivity. This is in this quarter, the only time we get molar absorptivity is when we're doing a Beer's Law problem. So we're like, cool, it must be a Beer's Law problem. It's a little bit of a different Beer's Law problem, but I'm going to go ahead and write down Beer's Law because I know I'm going to need it. A equals epsilon BC, where my concentration is going to be in moles per liter. Now when I look at epsilon BC, I'm like, well, hey, I've got epsilon, I've got A, so I've got A, I've got epsilon, I got B, because it's always 1, unless we're told otherwise. So in this situation, I could solve for concentration, which is going to be in moles per liter. Great, right? Then I say, okay, well, if I've got moles per liter, what good is that going to do me? Right now, I'm not even thinking about what answer I want to get. I'm just thinking about what I'm capable of doing in the problem. So, okay, if I've got moles per liter, well, it wants me to find the mass to get a particular absorbance in a particular solution. So that's kind of asking for a particular concentration. So this is kind of what it's asking for. But it doesn't want just the mass. It doesn't want just the concentration. It wants the specific amount of material to get that concentration. And whenever I see something that's asking for specific amounts, I generally try to switch to moles. Because we're in a chemistry class. I always switch to moles. The reason we always switch to moles is a really flexible thing. Moles can be turned into a concentration, it can be turned into a mass, it can be turned into a number of particles. It has this nice flexibility. So switching to moles is usually going to be something worth doing. Now, sometimes we do it and it's like, oh, I didn't even need to do that. But a lot of times getting the number of moles is going to give us a nice flexible thing. So I look at this and I say, okay, if I've got moles per liter, how do I get volume? How do I get, I just ruined that. How do you get moles? How do I get rid of liters and just get moles left over? Multiply by 1.74 liters. Liters will cancel out. That will get me how many moles I have. Now, if I have a number of moles, and I want to get to a number of grams, there's only one number that's given in the problem that I haven't used yet. What's that one number?
796.
Grams per mole. The units are important hints here, right? If I've got something that's grams per mole, and I multiply it, moles cancels out, and I'm going to get something in grams, right? Molecular weight is this relationship between how heavy for a certain number of molecules is grams per mole. So when I look at doing the math here, well, let's do it step. Okay, now that we've done our thinking, let's go ahead and do the calculation. So I'm going to have 0.585 is equal to 4.57 times 10 to the 4 times 1 times C. Do my rearrangement, 0.585 divided by 4.57 times 10 to the 4 times 1 is equal to C. Then I'm going to have C times 1.74 liters is going to get me my moles. And then I'm going to have my moles times 796.1, and that will get me my grams. And I'm going to do this all kind of as like one big calculation, again, to show you how mathematically it's like divide and then multiply twice, right? But that's not the hard part, punching stuff into our calculators. So mathematically, it's divide those two numbers, multiply by 1.74, multiply by 796.1. Right? This line in green here, that's all you got to do in your calculator. Figuring out that that's what you're going to do in your calculator is actually the important part, right? I know you can punch this into your calculator. Well, some of you are having trouble with the parentheses with the exponents still, but I know you can punch this into your calculator and get an answer. And then the last question we have, let's go ahead and get an answer, and then we can analyze that answer to see if it makes sense or not. 0.585 divided by 4.57 times 10 to the 4 times 1.74, whoop, not minus, times 796, 1.77. Anyone do the math yet? Now, if you're looking at your quiz, you might have different numbers because the numbers are randomly generated for each student differently. And here's the last clue we can look at, right? The units are clues. The units given in the problem, the units that it's asking for the answer in, it's all clues. I think it was only the first quiz where I was testing unit analysis where I did some weird unit requests. So paying attention to the units, it asks for the answer in milligrams.
Yes.
Right, so I look at this and I say, well, would milligrams make more sense? Instead of 1.77 times 10 to the minus 2, if I convert this to milligrams, that would be 17.7 times 10 to the minus 3 grams. And then milli would be 1 milligram is 1 times 10 to the minus 3 grams. So notice that the way I have this set up is the 10 to the minus 3 cancels out, and I get 17.7 milligrams. If I was going to report a number, which one do you think would be nicer to do? 1.77 times 10 to the minus 2 or 17.7? The units it asks for make sense in the problem with the answer you get. If you did this and you got 17 trillion milligrams, probably did something wrong, right? If you did this and you got 1.7 times 10 to the minus 6 milligrams, you probably did something wrong. But if you end up with like 17.7 milligrams, the units it was asking for is kind of a hint for what kind of answer you should be getting. Both of those problems were Beer's law problems, and they involved like this. Even though this is like divide, multiply, multiply, it's using 3 different like concepts for how we're doing this. This is Beer's law, concentration, molecular weight. This ties 3 different concepts together, and I got really lazy with my units to show you how the math kind of is just math. But the units help us kind of think about that and get us to the right point. So even though it's like, oh, it's mathematically so easy, getting to this math is the part that we need to focus on. How we read the problem, how we connect the concepts. Questions about this? So you came in, I don't know, did you have specific questions, general questions? Or?
Yeah, but it's about like newer stuff, so.
Okay, well, we're about to move on to 4.1, 4.2,
Okay.
if that's the kind of stuff where you had questions. People are focusing on the quiz, and then we can go on to other things.
Okay.
So if so we've done these 2 problems. If you have anything you want to add to the list, we can add to the list.
Okay.
And
I might be able to think of something.
yeah, otherwise, you know, we'll just keep going and see what we come up with.
After we do those problems, can we go over the formal charge stuff?
Yeah, we can add that to the list. We'll add formal charge to the list, and if anyone else wants to add things, we can add more things too. Good with quiz questions? You had the quiz questions, right?
Mm-hmm.
Great. Good? Okay. Always good to go and reflect on those past quizzes. I think you've all realized at this point that the commonly missed questions just keep coming back until they're not commonly missed anymore. So you can probably guess at some of the things that are going to be on the quiz tonight. But we'll get to that. Let's go ahead. Let's look at 4.1 questions. Number 3.
Yeah, for good. You should go fast. What type of bonding is found in the following compounds? NH4NO3.
Ooh. So this is where we have to start being able to recognize our polyatomic ions. And so one of the first things I realize is NH4. Do we know what polyatomic ion that is?
Ammonium.
That's ammonium. NH3, sorry, NO3,
Nitrite.
nitrate. Right, so when I look at this, I'm like, hey, here's a covalent compound. Here's another covalent compound. But they're going to be attracted to each other because there's a plus charge and a minus charge attracting to each other. So even though these are all nonmetals, because they're polyatomic ions, we end up with covalent, and then ionic attracting the cation to the anion. So this is going to have covalent bonding and ionic bonding in it.
If there's 2 of them together, does that always mean there's covalent bonding or not?
We have to be careful about that. If this was, well, in this, if it's if it's a positive cation with a negative anion, yes.
Okay.
We have to be careful because, honestly, my first hunch when I would look at something like this without knowing the polyatomic ions would be only covalent, because it's all nonmetals. And that's usually my tell for covalent bonding. Ionic bonding, I'm usually looking for cations and anions, which is usually a nonmetal and a metal. But here with the polyatomic ions, I've got a nonmetal anion, a nonmetal cation and a nonmetal anion. So the polyatomic ions kind of gives us this extra access to potential ionic bonding. That's number 3. Questions about that? Number 13. That's nice. I can just put a 1 in front of this.
Select the longest bond. Do you want me to give you all the options?
Sure.
Single bond?
Yeah.
Yeah, single bond O, H, F, H, I, and I.
Let's do a quick poll and see what people are thinking. 1 through 4. Which one do you think is going to be the longest bond? Question?
So the longest bond stuff, is that just how, like, the farthest on the periodic table?
Its biggest radius is the first thing we look at. Right? Biggest radius. So hydrogen, 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 iodide. When I look at the periodic table, iodide has a really big radius. So if I'm looking at an iodide to an iodide, big radius. It's going to be number 4. A couple of you had number 4 showing, so yeah. Ends up being number 4 for the longest bond.
It won't always be the one that's with itself, though.
No,
That's what I was, like, trying to
no,
figure out.
that's the weird part, right? So if this last one, we could add a 5th option. H to H is probably going to be the shortest bond because hydrogen has a really small radius. So we're going back to our radius periodic trends. And we're looking at, okay, H has a small radius to another H with a small radius. If this one was not an option, and we said, okay, which one's the longest bond? These are all H's for the first thing. I only have to look at the radius of the following thing and say which one has the biggest radius of this. Since iodine has the biggest radius, all the H's have the same radius, I can just focus in on that detail of the second part and say, oh, iodide with the biggest other radius, like with the biggest second radius, that's going to have the longest bond.
So does electronegativity, does that affect the bond strength?
Electronegativity has a minor impact on bond strength and bond length. It becomes more important when we start looking at particular considerations like up and down a periodic table. So if we were looking at HF versus HI versus HCl, but typically the change in radius is going to dominate over the electronegativity difference. The place where electronegativity becomes important is when you're looking at like HO to HF, where the radius is pretty similar, but the difference in electronegativity is significant. So those places where the radius is about the same for the ions for the atoms involved, that's where electronegativity becomes more important. It's only a few cases this quarter. It becomes more important when we get to Chem 129. We talk about it a little bit more. But for this, it's a relatively small effect. It's usually radius plays the bigger role.
And then is the trend for the radius on the periodic table left to right, it increases, or how does that work?
So there's the kind of two ways to think about it, right? We've got our kind of our high school thinking, which says the stuff here. Oh, I don't know, that's good enough. Things over here are small. Things over here are big. Put radius in there since there's other trends as well. It's kind of the opposite of ionization energy and electron affinity. But then the explanation, and again, I know you can all memorize that. The important thing that I really want is, can you explain why it's like that? Can you explain like why these things end up big from the idea of valence shells, Z effective? Can you explain why it gets small going this way, even though you're increasing number of electrons, right? This is more and more electrons. Why does increasing number of electrons get smaller? Core shell's not changing, number of protons is changing, right? You're not just adding electrons, you're also adding protons. You're adding them at the same rate, but you're not adding anything. You're not adding anything to your core electrons. So your shielding is essentially getting weaker and weaker, which makes it so things get pulled in more and more. So this I'm sure you can remember, but then the why does it happen that way is kind of the deeper thing we want to start to think about as well. Other questions?
Hydrogen is that like, where does that fall?
So this is another quirky thing that happens with hydrogen and helium, because hydrogen and helium kind of get tucked on the very top.
Yeah.
The N value usually has a bigger impact than going the side to side. So the N equals 1, hydrogen and helium are both really tiny.
Yeah. Okay.
Good for number 13?
Mm-hmm.
Let's check out number 14.
Let's just change it with the strongest bond.
Oh no, I erased it all. Oh, okay.
Yeah. I don't know if it's the same. Yeah, it's the same.
Let's check the same options again. So it was
Hydrogen, oxygen.
HO, HF,
Yeah.
HI.
Yeah.
Okay. Now, strongest bond usually goes opposite from longest bond. Longer bonds are usually easier to break. So when I look at this, I would guess that the I bond would be the weakest, not the strongest. I would guess HI would be second, and I'm kind of down to which one is stronger, HO or HF. And this is where that electronegativity idea does come in a little bit. So if I had to look at these, HF would have the shorter bond, but it's also got a pretty big difference in electronegativity. I still think that one's gonna end up being the strongest bond. Right, the HO being a little bit longer, but still pretty high electronegativity. I think HF with the really short bond becomes the hardest to break.
Okay. So you're saying it's the one with the biggest electronegativity?
Big difference in electronegativity. Small bond length, and a pretty big difference in. Now, yeah.
Does it have more to do with radius or negativity?
Radius usually has the bigger impact, right? And that's where the HO versus HF, I'm like stroking my beard thinking, because you run into this situation where the radius difference isn't that big. The electronegativity difference is kind of significant. It's like HF is very electronegative. Oxygen, well, HF is very, very electronegative. O is very electronegative, right? So there's still a difference in electronegativity there. And I'm trying to remember some slides from my other class to make sure I don't mess this up. Acidic strength increases. Yeah, no, that we're good. Okay. Yeah, so electronegativity, increasing electronegativity generally increases the bond strength. Stick with that for now. Smaller effect. I feel like I'm messing something up, but I'm not going to worry about it right now, even though I'm recording this and people might look at it for years being like, wait, that's wrong. I'll correct myself if I make a mistake, but I don't want to slow down the getting through problems right now. So.
And I don't need 25 because it's pretty much the same.
Pretty much the same? Okay. Does anyone want to see 25 on 4.1? Okay. HF, let me think about this. HCl is stronger, HI, HF, HO, HO is weaker. Usually increasing electronegativity. Yeah, increasing electronegativity increases acidic strength. Okay, because increases acidic strength. Increased electronegativity might make the bond weaker. I'm going to have to double check that. There's a thing I need to double check on how electronegativity affects bond strength. So if you wrote that down in your notes, put a big question mark next to it. If you wrote down increasing electronegativity increases bond strength, put a question mark next to that. I might have it backwards. And I just want to double check before I say for sure. So I'm going to get through these and then remind me to double check that.
Yeah.
Okay.
Really, I just like, so isomers, like just for those ones, if you're done, the isomers, if it's shifted, it's not an isomer, like it's just like flipped over.
Oh, is that number 25?
Like, well, no, it's like 14 is that. And I just want to.
Oh, 4.2 number.
Yeah, 14.
14. It's this guy.
Yeah.
Yeah, it's a really common question, so I actually already have it built.
Yeah.
If I can get this to
Yeah,
sit
that
right.
actually, yeah, that is it.
Right. So this is typically what we see. And what number 20, so an isomer, we need two pieces to define an isomer. Is this for number 14?
Yeah, this is 14.
Okay. So we need two pieces to define an isomer. 4.2, whoa, okay. So we need two pieces to define an isomer. We've got this thing that's like 1, 2, 3, 4, 5, 1, 2, 1. Something like that. I think this extra one's over here actually, right? So we've got something like this. I already have it made with my model kit because it's been such a common question this week. And to have an isomer, we need two things. We need the same molecular formula, but a different Lewis structure. And the problem with drawing this thing flat is we lose track of the fact that it can rotate in three-dimensional space, and single bonds can also rotate in three-dimensional space. So I could have also drawn it in this kind of like weird way. This looks very different from what we have there, but it's actually still the same, or I could even make it look more different if I do it like this. This looks pretty different from what we have on the board, but I didn't have to change any of the bonds. I didn't have to change the Lewis structure. I just need to recognize that there's like three-dimensional rotation. So it turns out, for that example, for 4.2 number 14, it's not isomers because it's the exact same molecule twice.
Yeah.
And for isomers, it needs to be same molecular formula, different Lewis structure. Not the same Lewis structure, just spun around. 4.2 number 8.
Yeah, this one I don't really know how. It's just saying whether two structures represent isomers. So that's kind of.
Ooh, what two structures are there? Can you just show me?
Yeah. I just don't get it because it counts up to the
Oh wait,
same
that's
thing.
the one I just did.
It might have been. I don't.
What was number 14?
14?
It's got a BR. 14 has a BR.
Yeah.
Oh,
BR.
so this one that I just did, that's number 8.
Yeah.
Right?
But how is that one shift? Like.
So if you look at this now, this is actually kind of like interesting. So let me just get it back to its kind of like neutral spot. Kind of like this. You see how that makes the Lewis structure that's drawn in there right now?
Mm-hmm.
And then let me see the second one. The second one is that. Right?
Yeah.
I didn't have to break any covalent bonds. Like it, probably if you're looking on the camera, this looks totally different, but it's actually not. It's just a couple rotations off. So it looks really different, but it's still the same thing. So it's not isomers because it's the same molecule twice, but we can make it look really different by accentuating like this longer chain down the middle.
Then how would you make an isomer of that one?
we would have to break a covalent bond.
Mhm.
So ready? Isomer.
Yeah.
Now there's no way I can rotate this and get it back to what we had before. Right? This is actually, wait, did I make an isomer? I didn't make an isomer. Hang on. Let's make it an isomer for sure. Okay. I made the same thing twice again. There. Now this is an isomer, right? Because there was nothing that had 4 carbons coming off of one spot.
Okay.
So now there's no way I can rotate this and get it back to something else. I actually made the same thing twice. Right? And this is one of the things we have to be careful of. This is a really common mistake when we're first learning to draw Lewis structures and isomers. I have students who are all the time, they're like, I'm going to take this aldehyde and I'm going to make an isomer by doing this. It's like, you know, that's the same thing still, right? You didn't actually make an isomer. You drew the same thing twice. To make an isomer, we need the bonding structure to look different. We need a different Lewis structure. And so that's what's happening in number 8. Now let's look at number 14 again and get number 14 correct. May I look at it real quick?
Or yeah. This is a great one.
Oh, same type of idea, right? This is, I don't have this one built already, but it's the same idea of like the rotation and through. Oh, it's a graded one,
Yeah.
so do you know if you
No,
got it
it's
right or
actually
not?
the same. It's the same. I did get this one right because I figured it out. But
Yeah, so it's the same. It's
I
the
just wanted
same
to-
idea of like rotation in
Yeah.
three-dimensional
I, like,
space
thought it
gets
was
the same thing back
exact
again.
Thing, but the other one looked less. Like I was more confused on the other one that you just
Yeah,
did
so
because
number
it
8.
looks different.
Number 8, yeah. So this one is not number 8 anymore. Let's see here. 4, 5. Number 8, it's because there's more carbons, it's easier to make it look very different. Even though two quick rotations, and it's like, wait, no, that's the same thing still. And it's just these 2 rotations is all it takes for it to look really different. Still the same thing though. Okay, that was it for the questions from the homeworks from last week. People were worried about the quiz tonight, so that's what we were going over. I also have a note to go over formal charge again, other concepts or ideas we want to go over. You said you had questions on the newer stuff.
I was gonna ask about midterm stuff, but I suspected like you probably went over that already.
No, actually, we've barely done any midterm stuff in office hours.
Okay.
So we can do midterm stuff as well.
Yeah.
We'll add that in. Do you have specific questions from it?
I mean, I'd like to do one of the problems.
Which one?
It was the section 3, number 1.
Okay, so that was free response number 1?
Yeah.
Yeah.
Yeah, it's like the 2-part question.
Yeah. 3-part question goes to
Yeah,
part
yeah.
C on the next slide. Okay, let's talk about formal charge and then we'll come back to the midterm. So if we're looking at formal charge, right, and for me, one of my favorite examples to explain the benefit of formal charge is the one we did in class yesterday, which is sulfate. Because sulfate is one of those things where when we make it, we can fill the octet, even though I don't like saying octet, I'm saying that on purpose to make it kind of wrong. We can fill the octet, we can get everything with 8s around it with all the right number of electrons, and we can make a Lewis structure that is completely wrong. And the real benefit of formal charge is being able to tell if we've made a lowest energy structure, if we've made the most stable structure. Those of you, I know you're not taking organic chemistry, but those of you who are going to take organic chemistry, you actually also care about you have the lowest formal charge structure, and you actually really care about the second highest, or the second lowest, because that's usually the reactive form of the molecule. So you care about the lowest formal charge, but then you also care about the second lowest, because that's where we get some really interesting reactions happening. So being able to recognize, is it the lowest or the second lowest, becomes important. So formal charge allows us to figure out that, like, oh, this should be double bonded, that should be double bonded. And that's going to give us the more stable structure. I'm going to try to come up with another example that we haven't already, oh, I've got one we haven't done in class. That's a good one to do. Let's do one that we haven't done in class. I wanted to do this as a reminder. And so we figured out that it's this one instead of all single bonds because that sulfur had the not good formal charge. So let's do one that we haven't done in class before. No, we haven't done in class before. to talk about formal charge. ClO3 minus the chlorate anion. So as a reminder, I have to pick things that don't have our nice pieces. We usually don't know how chlorine bonds to things. Usually it's just single bonds. So what do we do with a ClO3? As a reminder, there's a couple things we need for formal charge. Right. The thing that's best is having as many things equal to 0 as possible. Formal charge greater than +1 or formal charge less than -1. Right? That's going to be not likely. If we end up with a formal charge that's too big, too large positive, or too large negative, that essentially means that there's some really uneven sharing of electrons going on, and something is pulling electrons away from the other things in a way that's essentially overfilling its valence shell. It can happen, but it's never going to be the lowest energy configuration. It's never going to be a stable molecule. It might be a really reactive molecule, but it's not going to be a stable molecule, and we're looking for stable molecules. And then number 3, formal charge less than 0. Right, a formal charge less than 0 is often on the more electronegative atom. So when we're drawing our Lewis structures, if we had a choice between having sulfur be negative or oxygen be negative, we'll probably make the oxygen negative because it's more electronegative. Same thing here, as we draw this Lewis structure, if we have a choice between making the chlorine in the middle negative or the oxygen negative, we'll probably make the oxygen negative because it's more electronegative. And that's going to get us towards our most stable structure. Now what I'm going to do is we got time, right? The bell just rang. Okay, cool. So we've got plenty of time. Take a moment. Can you draw the Lewis structure for this? You're going to need that systematic method unless you remember a really nice trick. But do your best. Work with the people around you. Don't look yet. Do you remember the steps? Step 1, count valence electrons. Okay, let's do the steps. Step 1, count the valence electrons. Step 2, is propose a structure. This is where all of our nice pieces come in really handy. We propose really good structures, and we get it right on our first try. For something like the ClO3 minus, the chlorate anion, we don't really know the good pieces for chlorine. It's hard to propose a good structure on our first try. But generally, we have a general kind of thing that helps us with our proposal. We generally put the least electronegative thing towards the middle. It's because it usually bonds better. Right? So then we're going to fill our valence and get to our 8s. And then step 4 is we're going to check the formal charge. And we might need to repeat this. If we made a bad proposed structure, we might need to start this over and make a new proposed structure and try again. So the better we do on number 2, the less times we have to cycle through this and kind of go over and over and over and over. So the more we practice this, the better we get at proposing structures, the less we have to kind of do this guess and check work. I'll get it in a sec. So, with this in mind, go ahead and give it a shot. Draw something. Doesn't have to be right, just propose a skeleton. I'll do the counting here. So let's see here. Chlorine brings 7 electrons, and I've got 1 of them. Oxygen brings 6 electrons. I got 3 of them. A -1 brings 1 electron. So that's going to be 7. 6 times 3 is 18. 1, 26 electrons. My Lewis structure, whenever I'm done making it, and I think I've filled my valence and I'm all done, I better have 26 electrons around. Did I do my math right?
Probably. I was probably.
Okay, good. 19 plus, yeah, 26. We're just doing some formal charge review with a molecule we haven't done before for fun. So that's what they're working on right now, because I challenged them. If you want to give it a shot, you can. If you got questions you want to add to it, we've done all of these. We're about to go over a problem from midterm 1, and we can add more to it as needed. If you see one of the questions you already did on there, we can do it again in a little bit. I'm going to look at what you're all doing. Good start. Yeah. Right track, a little too many bonds, but you're on the right track. Good start. No, you're good start. Good start. Good start. Good start. I think too many bonds. We'll double check. Right track. I like this one a little bit more than that one, but we'll take a look. Good. Okay, so we're on the right track. Let's go ahead and do this together. You're all on the right track. You all have a reasonable proposed structure, and you're kind of ready to check your formal charge. So I'm going to just go ahead and do something that's a little bit wrong, but kind of similar to what you all have been doing. So I just threw in things until I got 8 to everything. This is not going to be right. I'm going to count to make sure I even have all 26. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. That's 26 electrons. If I checked my formal charge here, chlorine's going to be all messed up. The oxygens are going to be all messed up. This is not going to be my best structure. So let's actually use the formal charge to check that and see if we can predict how it's going to go. Our formal charge on chlorine is going to be 7 minus 2 minus a half of 6. The formal charge on that chlorine is +2. Ooh, that's not great. Question?
Why is there a lone pair in chlorine?
Just because I was filling my valence shells. I had to throw 26 electrons around. It shouldn't have a lone pair. But this was just my first, this was my first guess. And when I get a formal charge of +2, I can tell it probably shouldn't have that lone pair. I'm going to have to fix it.
Can you go over the process of calculating the formal charge for chlorine?
Yeah, so for chlorine, what I'm looking at is how many valence electrons did it start with? It started with 7 valence electrons. I'm going to minus the number of electrons that it has in lone are not bonding, so that's the lone pair there. That's where the -2 comes from. And then I'm going to minus off half of the bonding electrons. So I look at my 3 bonds. There's 2, 4, 6 electrons. So it's going to be 7 minus 2 minus 3, essentially. It's going to leave me with a +2 left over. And so I look at that and I'm like, that is too much positive. I don't want that, right? That's not likely. And so I'll go ahead and calculate the formal charge on my oxygen as well. That's going to be 6 minus a half of 2, since they all have single bonds. That's going to be -1. Formal charge of -1s on oxygens looks pretty good. It doesn't look bad, but it'd be nice if I could get a couple things to 0. Now, here's a little reminder trick that we can do to predict what kind of bonding structure chlorine is likely to have. If we think about the valence shell of chlorine, because the formal charge thing is essentially doing a valence shell check, chlorine is a 3s. Is it 3s or is it 4s? Fluorine chlorine is 3s. Okay. Right, and it's gonna have. Right, it's going to have 7 valence electrons, and it's going to have 11 openings. So I would expect chlorine to be able to form 7 bonds. And so when I start looking at this, I can say, okay, up to 7 bonds, because it's the smaller number between valence electrons and openings. And since it's only n equals 3, you can use that d orbitals to kind of get more openings than we would expect. And that was the big difference between oxygen, nitrogen, and fluorine versus phosphorus, sulfur, and chlorine, was having those d orbitals. So I don't need to stop when chlorine gets to 8. I can send chlorine higher. So one of the things I can do is I can switch that to a double bond. Now what I've done is I've forced this oxygen down to a 0, right? Because it's one of my nice pieces, 2 bonds, 2 lone pairs. And on chlorine, all that's changed is that 6 has gone up to an 8. So if that 6 has gone up to an 8, that plus 2 is going to become a plus 1 instead. So adding a double bond there has made chlorine closer to a good structure. And then I just do it again, right? I can do the same thing with this oxygen. Take that lone pair off the oxygen, say, what if that was actually a double bond? Now, 2, 4, 6, 8, 10, 12. I've got 12 electrons around chlorine. I got 1, 2, 3, 4, 5 bonds, and then a lone pair on it. But when I look at this, when I look at my calculation for this chlorine, this new structure, so this was my old one that I didn't like. For this new formal charge on chlorine, it's going to be 7 minus 2 minus a half of 2, 4, 6, 8, 10. That gets me a formal charge of 0. My chlorine has 2, 4, 6, 8, 10, 12 electrons around it, which is actually allowed because it's got this hypervalent situation, right? It's got the d orbital where it can put more of its electrons. And that's going to be the structure for the chlorate. We needed formal charge to show us that the first structure we tried was not the best way to arrange things, and that this new structure I'm proposing looks like it'll be more stable, right? Because I've got a 0 there, a 0 there, a 0 there, a minus 1 there. All of my formal charges add up to the minus on the chlorate anion. And so this looks reasonable.
Why can't we add another double bond to that last oxygen?
Another double bond to this last oxygen. So that would make this one 0. And then I would have a new formal charge on chlorine. The formal charge on chlorine in that case would be 7 minus 2 minus a half of 2, 4, 6, 8, 10, 12. That would get me minus 1. If I look at number 3, so this is actually a valid Lewis structure. It's probably actually one of the excited states of the chlorate anion, but it's not going to be the lowest energy, most stable state, because we'd rather have the negative charge on the thing that's more electronegative. We'd rather have it on one of the oxygens. So this is actually probably, chlorate probably exists in the natural world like this some of the time if we heat it up a little bit or electrify it or something, give it some energy. But generally, oxygen being more electronegative, it's more likely to be like that, where this oxygen ends up with the -1 instead of the chlorine ending up with the -1. So not unreasonable, but probably not the lowest, most stable. Question?
So like, in general, like the priority is making the least electronegative / like middle atom the most stable when you're building a molecule.
Generally, well, the most important thing is to get our full valence shells for the things that we can. So getting our oxygens to 8, our nitrogens, our carbons, getting those to 8 electrons around them, and then trying to get as many electrons as we can around if it's phosphorus chlorine or sulfur, trying to get as many electrons as possible around them.
But the
But-
middle one should be filled first.
The middle
Right.
one, not always, right? So when I'm looking at this, the chlorine is not actually all the way full because it can go up to 18 electrons, right? It's the oxygens, the nitrogens, and the carbons. Getting those to 8 is usually the higher priority, and then kind of going through: do I have good formal charges? Do I have as many formal charges equal to 0 as possible? Do I have things that are not too big or too small? Do I have the thing that's more electronegative with the minus charge? So the place where your logic is close to correct is the fact that since we generally have the lower electronegativity thing in the middle, it usually ends up being 0, right? And it's usually things around the outside, oxygens around the outside, usually end up with the minuses.
Wait, why is that? That's what I'm lost.
Because usually when we're proposing our structure, we usually put the least electronegative thing towards the middle. So that's putting the electronegative thing in the middle, and then the more electronegative thing usually gets the minus. So it's these two things working together that make it so the middle usually ends up going towards 0.
Okay.
Doesn't always happen. There's some nitrogen containing compounds where we end up with +1s in the middle, but this is pretty common.
Is there like something you should recognize for when that happens? Like to know that's gonna happen, or is it kind of just like outliers?
Kind of outliers, right? A lot of the stuff we're doing when we're doing our formal charge calculations, all of this stuff is a little bit on the outlier side.
Okay.
80% of the time are good pieces for drawing Lewis structures that we learned last week. That's usually enough. 80% of the time, that's all we need to do. And it's just these outliers where we're like, whoa, we got a whole separate process that we took like an hour to do for these outliers, even though they're not that common. They're not that common, but when they show up, they're really important. All set?
Yeah. Thank you so
See you
much.
later.
So when you're calculating, like, so when you're calculating the formal charge of oxygen, is the reason you're doing the 6 valence electron minus 6 lone pairs is because you're not counting the ones that are full?
I'm just looking, so I just did this one,
Mm-hmm.
right? So I did my formal charge on oxygen. I usually like to put a label if this is my formal charge of oxygen with 1 bond. So I'm not looking at the oxygen with 2 bonds. I'm looking at the formal charge of oxygen with 1 bond. And so it starts with 6 valence electrons before bonding.
Mm-hmm.
After it bonds, it has 2, 4, 6 electrons in lone pairs. That's 6 electrons that are not bonding, and then 2 electrons in the bond.
So you pick the one with the single bond?
Yeah, I picked the one with the single bond. Why didn't I do it the one with the double bond?
Because you know they're...
I've done it so much I already knew it was 0.
Okay.
Right? If we did the one for the oxygen with the double bond, and again, it's just because I've done this so much, formal charge on oxygen with the double bond, I recognize I'm like, oh, that's one of my good pieces. It's probably going to be 0. Right? It's 6 minus 4 minus a half of 4 equals 0.
Okay. So then, say when they ask you to calculate overall charge, is that all of the...
It's like all the formal charges added together.
Oh, okay.
Right? So in this case, it's 0 plus 0 plus 0 plus minus 1 ends up with a minus 1 overall charge.
Okay.
Feeling good about that? Ready to try that midterm problem?
Yes.
Okay. Let's do it. I'm not going to have you read the whole thing to me. So this was, at its core, this is a concentration problem. This is just asking us to calculate concentration. But I did it in the context of hemoglobin, because I know there's a lot of people in the class that are animal science or bio. And so I tried to put it into a context that was more relatable, things that you're going to have to do in the future. And I actually talked to someone who was a bio major, and they're like, oh yeah, all the time. All the time you're going to be calculating concentrations. They said the most frustrating thing is the fact that you have to switch between different concentration units depending on which thing you're doing. We're only doing molarity in this class, but there's a lot of different, there's molarity, there's molality, parts per million, percent by weight, percent by volume. Like there's a lot of different ways we talk about concentration. We're only using one of them this quarter. So the bio people I was talking to, they said the frustrating part was learning how to convert between all of the different ones. So they're like, you're only doing molarity? Easy. Easy for them because they've been doing it for a couple of years already. But so this problem, I'm actually here. I'll just go ahead and read it real quick. So this problem is all the hemoglobin stuff, right? Hemoglobin's important. It's in blood. It's important for the way we exist, and yada, yada, yada. A healthy human has a range of hemoglobin concentration, mass of hemoglobin, has a mass of hemoglobin between 10 and 12? Oh, which version did you have? Did you have the 10 to 18 or the 12 to 20? There were different versions.
12 to 20.
Okay, so we got 12 grams to 20 grams in 100 milliliters of blood. Given that the protein, so hemoglobin is this giant molecule. Most of the things we look at when we're looking at molecular weights are these kind of small things. This thing has a molecular weight of 64,500 grams per mole. It's made of a couple thousand carbons, hydrogens, and oxygens. This is this huge molecule, right? It's a protein. It's got like these long strands. It's got a lot going on. That's the molecular weight. And then it says, what would be the concentration in molarity of hemoglobin in a healthy human? So part one is so we got to get to molarity. So this is, again, one of those situations where when we see the math at the end of it, we're like, are you kidding me? That's it? But the process of getting to that math becomes the important thing. So let's look at a couple things that we have going on. I'm going to go ahead and do it in my typical way when I don't know how to start a problem. I'm going to look at, well, I've already got the explicit information, so I'm just going to look for the implied stuff. One thing is I need to know that molarity equals moles per liter. I need to recognize that 100 milliliters equals 0.1 liters, which means I already have my volume. So that just means I need to find the moles somehow. How do I find the number of moles?
Molar weight.
What do I do with the molar weight? So molecular weight, I can just use the units that are given to say molecular weight is grams per mole. If I want to get moles alone, I just rearrange this equation. I'm going to do this mass per unit of mole. If I want to get the moles alone, I just do a rearrangement of this equation. So it's moles equals mass divided by molecular weight. That also makes sense because if I want to get moles, you notice my moles is on bottom? That means I need to flip this number over. I need to divide by it to get moles on top. So I do this rearrangement and I say, great, I can get 12 grams divided by 64500 grams per mole. That will get me my number of moles. Then I just take that divided by 0.1 liter. That gets me my molarity. So mathematically, when we go through all of this thinking, we start kind of putting this together. We recognize mass divided by molecular weight gets me my moles. Moles divided by liters gets me my concentration. The algebra, it's not even algebra. The calculation we need to do is just 12 divided by 64500 divided by 0.1. Right, and when I put it like that, it feels like mockingly simple. And it's like, take that number, divide that number, divide that number. It's like, and it's really almost like fiendish of me to be like, that's it, that's all you had to do. It's like, we all know the math isn't actually the hard part, right? The math, plugging things into the calculator, is not the hard part. Realizing what we need to do, so this becomes 1.86 times 10 to the minus 3 molarity. 1.8 millimolarity if we wanted to put it into like different units. But 1.86 times 10 to the minus 3 molarity, right? And then we say, okay, that's a reasonable molarity. We've seen things on the micro scale. We've seen things on a larger scale. But that's how we calculate the molarity. We do the same thing, change that 12 to 20. So that's the low end of the concentration. Change that 12 to 20 to get the high end. So let's go ahead and let me write that number down because we didn't get to number 2 yet. So our molarity range is going to be 1.86 times 10 to the minus 3 molarity for our low end. And then if I go ahead and do 20 divided by 64500 divided by 0.1, we get 3.10 times 10 to the minus 3 molarity for our high end. Again, the important part is recognizing how molarity, so there's 2 important parts here. Recognizing how molecular weight relates to moles, and then how moles relates to molarity. So it's not a trivial thing, kind of having those realizations, especially since for a lot of you, this is the first time you've been working with molecular weight, this is the first time you've been working with molarity. It's not trivial. It takes some practice, it takes some thinking, it takes some figuring out how to pull problems apart. Questions about this before we go to the second half of the question?
It's the one part I got right.
Okay. This part is?
Yeah.
So so it's the second part, the number of molecules that you had trouble with?
Yeah, and then the absorption spectrum.
Oh, the definition parts. Okay. So let's go ahead and let's go to part 2 of this. Part 2 says, how many molecules on average do you have in a human if they are 5.2 liters? I gave it in milliliters, I just did the conversion really quick. So, again, we got kind of 2 things to think about. I want a number of molecules, so that's going to be my number of moles times Avogadro's number equals number of atoms, or molecules. So I need to find that n again, recognizing that molarity equals moles over volume. Rearrange that, molarity times volume equals moles. So I'm going to take the average of those 2 molarities, multiply by 5.2, multiply by Avogadro's number. So 1.8 and 3.2, this is going to be like a 2.7 average. 1.86 plus 3.1 divided by 2, 2.48. So we have 2.48 times 10 to the minus 3. Our average is 2.48 times 10 to the minus 3 moles per liter. Multiplied by the average human body volume of 5.2 liters of blood. Gets me 1.289 times 10 to the minus 2 moles. Then I have to recognize the 1.289 times 10 to the minus 2 moles times 6.022 times 10 to the 23rd molecules per 1 mole. So moles cancels out, and that will get me how many molecules? 6.022 times 10 to the 23rd. Of course, I get a giant number, 7.7 times 10 to the positive 21. Because there's a giant number of molecules in a human body. What did you get?
7.7 to 27. I don't know
Huh.
how. I think maybe I try to convert the molarity or something, like from U moles, or I try to switch it to U moles.
You might have done a U moles. You might have done something wrong with the liters. You got most of the credit for that still, right?
Yeah, I think so.
Let me take a look.
I mean, it's just circled, so I think
Yeah. You got most of the points.
and then I was just lost here.
Okay, so for this one, so if we go to part B, this is Are we ready to go to part B? Is that okay? Question first, yeah.
Can you explain how you got the 2.48 times 10 to the negative 3?
That was add these two together, divide by 2.
Oh.
Just take the average of them. Some other people did the masses add together divided by 2. It's a little bit easier, gets the same idea. Okay. Other questions? Okay, so then we're going to go to 1B. I think we need, this is, we're going to need that 2.48 times 10 to the minus 3 molarity if memory serves. So let me write that down before I erase it. 2.48 times 10 to the minus 3. And so the second one was, hey, we've got this plot. It's got the hemoglobin, and it's got the oxygenated hemoglobin. It says, using the absorption spectrum of hemoglobin shown below, and your answer to part A, what would you calculate for the molar absorptivity of hemoglobin at lambda at max equals 440 nanometers? The black line with triangles is the hemoglobin, the gray line is the other thing. So I kind of put 2 steps to this so that way I could know what you were using in your calculation. If you just take a line across from the top of that black line, absorbance is approximately equal to 1.4, right? So then we say, okay, well, if I've got an absorbance, I've got a concentration. It's asking me to find molar absorptivity. Which law do we use? Beer's law. We're going to have absorbance equals epsilon BC. It's going to be 1.4 is equal to epsilon times 1 times 2.48 times 10 to the minus 3. Now we just divide over. 1.4 divided by 1 times 2.48 times 10 to the minus 3. Let me see, what did you do?
I didn't even think to use the concentration.
Oh yeah, you threw wavelength in there, which is that's one of the common mistakes that we talked about when we were first doing Beer's law. So we get a value of 564.5. A little bit lower than we usually see for our epsilons. Epsilon's usually 10,000 to 100,000, but that's for like dyes. So this is lower than we usually see, but this is the absorptivity of hemoglobin in blood. I actually, if memory serves, like I based this off of actual experimental data. Like the plots I got, I actually looked up someplace. I should have put a reference. Sorry, don't tell. Yeah, so this is probably pretty accurate. So one of the most common mistakes that people make in this is they mix up path length with wavelength. And so it looks like that's what you did with the 440 times 10 to the minus 9 getting dropped in there and kind of really throwing off what this means. And I think if you do that, you end up getting a really kind of nonsensical answer for this when you start to divide it over.
Yeah.
So.
And then, what was it asking for? It says estimate absorption.
So it was just so you could write down your estimate of the, so like from the graph.
So this is supposed to be the 1.4?
Yeah, so you put 1.59 times 10 to the 9.
I think I was in a row. This is like the last thing I did.
The last thing you did, yeah. So I was just looking for this 1.4.
Yeah.
Just your estimated absorption. And the reason I did that was because I wanted to have like at least 2 steps. So like when somebody did their calculation, I'm like, wait, how the heck did you do this? I'm like, well, what was your estimated absorbance? So if you used 1.4, we're working from the same numbers. If you put 1.3 or 1.5, then I can know why our numbers are off a little bit. If you put 200, I can be like, wait, where'd you get that? Like, what's your idea of absorbance? Do you also want to talk about part C?
I can't tell if
Let's see,
I
what
think I
you
got
mean.
partial credit for it.
You got partial credit. You got about half credit. You got almost full credit on number 2. You got about half credit on part C. The main thing, and this was in the definition of epsilon, epsilon depends on 2 things. The main thing is it depends on the identity, right? It's a property. Right? if you remember, we talked about epsilon, molar absorptivity, really close to where we were also talking about density. And I like using that analogy because density changes. Density doesn't change if you cut something in half. If I've got a brick of gold, it's got a certain density. If I cut that brick in half, the two chunks have about the same density because they're both still gold. Their masses are less because it got cut in half. Their volumes are also less because density is that ratio of mass to volume. And it turns out epsilon is kind of the same way, where it doesn't depend on A. Epsilon is a ratio of A to C. It's a ratio of absorbance to concentration. So if your absorbance cuts in half, your concentration must always also be cutting in half. If your concentration cuts in half, your absorbance must also be cutting in half, unless you change the molecule. Right? If you switch from gold to silver, now you're talking about two different materials with two different densities. If you change from blue dye to red dye, you're talking about two different molecules with two different epsilons. If you switch from hemoglobin to oxygenated hemoglobin, you've actually changed the molecule and the way it interacts with light. It's like you've got a whole new compound in there because of that reaction. And so we see that in the fact that the peaks shift in that plot from the hemoglobin to the oxygenated hemoglobin. And the most common answer I got for that part was people kind of doing a description of how the graph changed. They're like, oh, it shifted down in wavelength and down in absorbance, and that's what it does. And I was like, but why? Why does it do that? And it's because when you react, when you add that oxygen in, you're changing the identity of the material. It's like a new material, so it has a new epsilon, and we can see that in the way that its absorption coefficient changes because we've changed the identity of the material. Adding oxygen in doesn't change it dramatically because it's just a little shift over, a little shift down, but it does change it. And so you can actually, and here's the cool part that we didn't get into in this problem, is you can actually they have these like UV things where like you can put your finger on and they can like get your like blood oxygen levels. It actually works through the absorbance differences between oxygenated and deoxygenated and oxygenated hemoglobin and regular hemoglobin. It can actually detect that through your skin and doesn't have to draw blood to do it by looking at the different absorption of the different wavelengths, which I think is so cool. And I didn't get into that part because I thought I was overwhelming you enough already.
So was part C out of 9?
Yes.
Okay.
A, B, and C for question 1 were 9 points each. And then question 2 was out of 10 points. Other questions about that midterm part? Has anyone figured out how to decipher my special little like marks codes?
Kind of.
Circles are like half credit. Underline is like you made one little mistake someplace. Check marks are full credit. Circles with slashes are like, I'm probably giving you points because I feel bad for you. I mean, you didn't put it blank. You put something that had some rationality to it. It wasn't just like nonsense. I gave you the points I could. Hey, how's it going?
Hi. I just have a question on one of the questions for LabPal.
Sure. I'm recording, by the way, but we can go ahead and do that. Are we ready to move on?
Yeah.
Let's look at this LabPal question. Which one is it?
It's 29 from 5.1. It's like drawing the resonance of the sulfur molecule.
May I take a look?
Yeah.
So, we got sulfate. What's actually question 9? Can I look at question 29 by any chance? See what it says? Okay. So it says draw one of the resonance structures, resonance contributors to the minimized formal charge on the ion. Include all lone pairs. You'll need to add charges using the plus or minus menu, where you also get the lone pairs. So you went in and added hydrogens. Don't add the hydrogens. This is not H2SO4. This is just SO4. Yours should just be that. That looks fine.
I had a question with the formal charge. Because sulfur breaks that octet rule, how many, like if it were to ask about the formal charge, what would that be?
So when we look at this, the way we calculate the formal charge, whether it's breaking the octet or not, the formal charge on sulfur is going to be calculated the same way, which is valence electrons before bonding minus non-bonding electrons after bonding minus half of the bonding electrons after bonding. Right, same equation we use whether it's following the octet rule or not, right? Because it's still like, whether we call it octet rule or not, it's really the closed shell rule. So formal charge is going to be calculated for hydrogen, which has a closed shell of 2 electrons, we would use this. For nitrogen, oxygen, fluorine, carbon, which have a closed shell of 8, we use this. For phosphorus, sulfur, chlorine, which have a closed shell of 18, we still use this. Even though it has that bigger valence shell with the d electron, the orbitals that are empty, we still use this. So let's go ahead, let me draw, tell me if I'm drawing the same sulfate you had. If memory serves, you had it like this?
Yeah.
Did you have lone pairs on everything like this?
Yeah.
Like this? Okay. So if we go ahead and calculate the formal charge of sulfur in the middle there, I'm going to do valence electrons. Sulfur has 6 valence electrons before bonding. No lone pairs on the sulfur, so that's going to be 0 non-bonding electrons, minus 1/2 of the electrons in the bonds, 2, 4, 6, 8, 10, 12, half of 12. It's just, the thing that's different is this number can be bigger than 8.
I guess my question is like, because sulfur can go to like 18,
Yeah.
wouldn't there be lone pairs on the sulfur?
We ran out of electrons. So,
for
right,
the entire...
for the entire molecule. Now, we could say, oh, what if I do this instead? Right? We can propose other structures and say, look, this makes it, and we talked about this a little bit earlier as well, so if you go back, it's in the video, I'm going to post right after this, but we can say, look at this. Oxygen 0, oxygen 0, oxygen 0, oxygen 0, sulfur is still not to 18. This looks like it could be better. Because when I calculate my formal charge in this proposed structure, my formal charge on those oxygens with 2 bonds is 6 minus 4 minus 1/2 of 4. It's always equal to 0. But if I go and calculate my formal charge on the sulfur here, I'm going to have 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12, 14, 16. And that's going to give me a formal charge of minus 2. What that essentially means is this sulfur has somehow been able to pull extra electrons away from the oxygen towards it, even though it's less electronegative than oxygen. And not just a little bit, it's essentially pulling 2 extra electrons towards it. Really unlikely. And so it turns out that the more stable structure is going to be this one, where if I had more electrons to throw around, maybe I'd put some lone pairs on there. We do see that in things like H2S, where sulfur is the most electronegative thing in the molecule, we see sulfur end up with lone pairs. But in this situation where sulfur is not the most electronegative, when oxygen is there and more electronegative than it, it kind of gets its lone pairs pulled away by the oxygens into the single bonds and double bonds.
Okay.
Does that make sense?
Yeah.
Okay.
Thank you.
You bet.
I was like,
I'm going to go ahead. I think that's most of the questions. I'm going to stop recording so I can get this started posting. But I'll keep answering questions. Well, actually, maybe not.